Section 5.4 is about medians and altitudes, and we'll discover two more points of concurrencies when it comes to the medians and the altitudes. So to start, let's first define what a median is. A median of a triangle is a segment from a vertex of a triangle to the midpoint of the opposite side. So just looking at this rough sketch of a triangle at the bottom, a median would go from a vertex, like right here, to the midpoint of the other side. So here would be the midpoint of that side, indicated by these two sides being congruent. So we would go from this vertex and drop a segment down. So that red segment would be the median from this vertex to that other side. The point of concurrency of the three medians of a triangle is called the centroid. The centroid always lies inside the triangle, and a triangle will balance at that particular point, at the centroid. That is called the center of gravity. So again, if you were to find the centroid by finding all of the medians of each vertex, and you cut out that triangle, you could actually balance that triangle at the centroid at that point. And again, that's called the center of gravity. I would write that down in your notes. The way I remember it is, it's the center of gravity and it's the centroid. Centroid, center of gravity. I would write that down in my notes as well. Just like in the last two sections where we talked about the concurrency of the perpendicular bisectors and the concurrency of the angle bisectors, we also have the concurrency of the medians of a triangle theorem. It states the medians of a triangle intersect at a point, and then remember that point is called the centroid. That is 2/3 of the distance from each vertex to the midpoint of the opposite side. So in the diagram here, we have P is the centroid because it is the point of concurrency of all of the medians, the blue lines of the triangle. So again, we would call that the point of concurrency of the medians, and we can call that the center of gravity since it is the centroid. So according to the theorem, we have this first statement. AP is equal to 2/3 of AE. So again, AP is equal to 2/3 of AE. So the length of AP is 2/3 the length of A to E. BP is 2/3 the length from B to F. So BP is equal to 2/3 times BF. And our last one, CP equals 2/3 of CD. So the length from C to P is 2/3 of the length from C to D. Make sure all of this is written in your notes as well, especially the stuff about the 2/3. Since we'll be dealing with fractions in this section with this theorem, here's a reminder. Dividing by a fraction is the same as, make sure you have that written down as a reminder in your notes as well. Dividing by a fraction is the same as multiplying by the reciprocal. So here's an example. If I wanted to take 4/3 and divide by 1/6, that's the same thing as 4/3 times 6/1. So then all you got to do is multiply straight across, or you could do some cross simplification. 3 goes into 6 twice. So we end up with 4/1 times 2/1, which is just 4 times 2, so I get 8. So again, multiplying by the reciprocal is the way you can get rid of dividing by a fraction. Example number 1, in triangle HJK, P is the centroid and JP is 12 units long. Find the length of PT and JT. So let's first think about our relationship between JP and JT. We know from the concurrency of the medians theorem that the length from J to P is equal to 2/3 of from J to T. So let's fill in what we know. We know that JP is 12. So filling that into our equation, JP is 12 equals 2/3 times JT. I have to find JT. So the first thing I'm going to do is divide by 2/3. Remember, dividing by 2/3 would be the same thing as multiplying by the reciprocal, 3/2. 2 goes into 12 6 times, so I basically just have 6 times 3, which is 18. So JT is equal to 18 units. If JT is 18 units long and JP is 12 units long, you would know then that PT is equal to 6. Now looking at this, if you noticed, we ended up with 6 units right here. half of 12 is 6. So if this length is 12, you can find the other length just by dividing by 2. So half of 12 was 6, and then if I just add those two numbers together, then I would get that total length. So instead of doing all this fraction work, you could just use some logical sense. If you get this segment, you know that half of it would be that remaining segment, that 1/3, and if you add those two together, you end up with the total segment. So there's a shortcut you can do that way. If this way makes more sense, go ahead and do it that way. Example number 2, the vertices of triangle ABC are A, 1, 5, B, 5, 7, and C, 9, 3. Find the coordinates of the centroid of triangle ABC. So the first thing I'm going to do is just plot my points. So those are my 3 points, and so I'll connect them now so I can form triangle ABC. Remember, the goal of this problem is to find the coordinates of the centroid. Thinking back to the last theorem, we know that the centroid lies 2/3 of the way between the vertex and the midpoint of the other side, so 2/3 of the median. So if we were to just find the coordinates of one of the midpoints of one of the sides and draw that median, find the length of that median, then we would be able to do 2/3 of it to find where exactly that centroid would lie. Looking at the sides of this triangle, it looks as if the centroid would be a vertical line if I went from vertex B. If I did it this way, I'd have a diagonal line, and if I did it this way, I'd have a diagonal line. So again, I'm going to try to find the easiest vertex to go off of. So again, it looks like the median would go from vertex B here, and this would be the midpoint. So the first thing I want to do is actually verify where the midpoint of segment AC is. So I'll use the midpoint formula. Remember, to find a midpoint, you add the x's together and divide by 2, and then you add the y's together and divide by 2. So to find the midpoint of AC, I'll add 1 to 9 and divide by 2, then add 5 to 3 and then divide by 2. Simplifying that, I would get 5, 4. So let's plot that on our graph. We'll call it point M. So going over to the right 5 and up 4, I found the midpoint of segment AC. Notice that from vertex B straight down, we would have a vertical line. So again, our estimation was right. We do have a vertical line from vertex B to the midpoint of AC. So the centroid would lie 2/3 of the way down that line. That line is 1, 2, 3 units long. So the centroid would lie 2/3 of that way. So BM, again, is 3 units long, and the centroid is 2/3 of that. 2/3 of 3 is 2. So that means starting from vertex B, if I go down 2 units below it, I would find the centroid. So again, going 2 units down from vertex B, I would find the centroid. So that would put me at this point right there. And remember, we were supposed to find the coordinates of that point. So I would count to the right 1, 2, 3, 4, 5, and up 1, 2, 3, 4, 5. So the coordinates of the centroid would be at 5, 5. Before we can move on, we have to talk about some more vocabulary. The altitude of a triangle is the perpendicular segment from a vertex to the opposite side or to a line that contains the opposite side. So here are 3 examples where we have an acute triangle, a right triangle, and an obtuse triangle. So the first thing it says is classify the triangles by its angles, then draw the altitude. So again, this first triangle is an acute triangle. To draw the altitudes, I just start from one vertex and drop a straight line down so that it is perpendicular to the other side. And then those would be the other 2. Notice that they all intersected at the one point, so it has a point of concurrency, and in an acute triangle, it was inside of the triangle. Next, we have a right triangle. So to draw the altitudes in this one, I would have to take from this vertex and drop a straight line down. But notice that when I draw this altitude, it ends up being that leg itself, since this leg is perpendicular to the other leg. Same goes for this vertex. If I drop a straight line to the other side, ends up being that exact altitude is that leg. So the only altitude that we can actually draw is from the right angle to the hypotenuse. So it would end up looking like that. And just remember, each leg ends up being an altitude for the acute vertices in the right triangle. And finally, we have an obtuse triangle since this is 110 degrees. To draw the altitudes in a obtuse triangle is a little bit more difficult. Notice that if I start at this angle right here, A perpendicular line would be down this way. So I actually have to extend this line outwards. So this altitude is actually outside of the triangle. So it would end up looking like that. Look at another one. Going from this vertex, a perpendicular line down would be going this way. So again, I'd have to extend this line outward and it would look like this. So again, notice it is outside of the triangle. And finally, if I were to go from the obtuse angle, perpendicular line down to the other side, it would look like this. And that's the only one that actually ends up inside of the triangle. So again, notice that the acute triangle, all of the altitudes intersected inside of it. The altitudes actually intersected at the right angle here because all of them came together at the right angle. And then if I were to extend the ones in the obtuse triangle, they all intersect outside of the triangle. So again, an acute triangle, the altitudes intersect inside. In a right triangle, it actually intersects at the right angle itself. And in an obtuse triangle, it intersects outside of the triangle. And that brings us to our last theorem, the concurrency of altitudes of a triangle. This is much like the concurrency of the perpendicular bisectors, which is called the circumcenter, the concurrency of the angle bisectors, which is called the incenter, and the concurrency of the medians, which is called the centroid. Each one of those has something special happen at that point of concurrency. The concurrency of the altitudes does not have anything special about it. It's just called a certain point. So the concurrency of the altitudes of a triangle states the lines containing the altitudes of a triangle are concurrent. So all this is stating is that when you draw the altitudes of a triangle, no matter if it's acute, obtuse, or right, those three altitudes should meet in a point of concurrency. That point of concurrency of the three altitudes of a triangle is called the orthocenter. And as we saw in the last slide, the orthocenter can either lie on the inside, on, or outside the triangle, depending on if it is acute, right, or obtuse. And again, there's nothing special about the concurrency of the altitudes, like the concurrency of the medians, where it lies 2/3 of the way down of the median itself, or that the circumcenter is equidistant to the vertices of the triangle, or the incenter is equidistant to the sides of the triangle. The concurrency of the altitudes just is what it is. It's just called the orthocenter. And that's it for this section. Make sure you jot down anything that I said that you needed to make sure you have written down, and anything else that you're not sure about so that we can talk about it in class before we move on, and we'll see you then.